So we are delighted to have all the way from Canberra, where it is now very late, Dr. Michael Anenburg from ANU. So, Mike, I'm just going to let you get on with it. Keep everything on time.
Yeah, sure. So regarding the question that was asked in the chat, I think I will answer it because answering that may help a bit with the things I'm talking about. So scandium and yttrium are considered sometimes as rare earth elements, but they are not lanthanides. Okay, which means that especially for yttrium, even though it behaves very close to how all of the lanthanides do, it doesn't do that all the time. And if you try to plot it on this ionic radius plot, then there's a question of where does exactly it fit? Because again, it is not a lanthanide. So very often people consider it to be as very similar to holmium. And looking at yttrium to holmium ratios in all kinds of rocks or minerals or whatever can be very informative. So there's the mantle value of about 25. So yttrium over holmium is 25, and any deviation from that will tell you something. So that's something that can be taken into account. Not to me, not now. About scandium, it's not a rare element. I mean, there's no way how you look at it. It doesn't behave the same. It doesn't occur in the same places. So there's not much to say about it. However, it is used in all of those spidergrams where you have a bunch of a set of 40 elements, and then you normalize them to either chondrite or a mantle or whatever, and then look how that deviates. Yeah, so I will start now. I'll share my screen, and I will start. So yeah, thank you so much for inviting me. It's really fun to be here. If you want, you can minimize my face in the corner because my face is not as interesting as the things I'm going to talk about. Reference patterns and what we can do with them. So the thing I'm going to show you now, all of that was developed by Professor Hugh Neal here at the ANU, and he published that in a paper about 5 years ago in Journal of Mineralogy, which introduces a lot of those concepts. It shows examples, especially for basalts. So that would be, if you're interested in the topic, that's a really good paper to read. It's a bit long. I think it's more than 40 pages, but it's very informative. So reference patterns. Here are 3 reference patterns. We have pattern A, B, and C. And when you look at them, what differences do you see? Okay, so you see that all of them are kind of light reference enriched because lanthanum, cerium over here are higher than terbium, lutetium, thulium over here. You can see that maybe pattern B is concave, pattern A is convex, okay? Pattern C is kind of sinusoidal or sigmoidal, however you want to call it. And you can talk a lot about them. You can describe them in words, you can describe them in figures, but what if you would like to describe them with some kind of quantitative measure, quantitative number that gives you information about what it looks like or what are the properties of the patterns? So, a very common parameter is lanthanum over lutetium. Okay, so we take this, divide by this. In our case, this here is about 1,000, this is about 1. So we have something about 100. So it tells you, yes, that we have much more lighter reference than heavies. Again, on a chondrite normalized plot, this was not directly translate to ppm or %. But all of them, all of those 3 patterns have exactly the same lanthanum to lutetium ratio. So it doesn't actually tell you much about the shape. Well, in that case, we can try something different. We can try a ratio like lanthanum over samarium. In this case, pattern B here, we take this lanthanum here, this samarium here, and the ratio would be about 1, okay, for pattern B. For pattern A, our samarium is here, which is about 10, so 1,000 divided by 10 is about 100. So this is much more informative. Now we have a different number that describes different reference patterns. Okay, and what about pattern C? So samarium is over here. Okay, so for pattern C, we'll have a number in between. I know it's in log scale, so it's a bit hard to see, but let's say for the discussion that it is 10. Okay, but there's a problem here, because even though it's 10 and it does tell you what the lanthanum to samarium ratio is, it is not unique, because I can draw a rare element pattern that looks like this, and it will have exactly the same lanthanum to lutetium and lanthanum to samarium ratios as pattern C, but it's not the same pattern. It looks different. It has different concentrations of all kinds of rare elements. It represents different fractionation processes or different information. So this is a problem. Let me show you another problem. So here are rare element patterns, and let's start by looking at A. This is how a garnet might look like. So this is a very typical pattern for a garnet, and very steep for the light rare earth elements and almost horizontal for the heavies. And in here, I have all kinds of different measures like that. Lanthanum to lutetium, lanthanum and samarium, have gadolinium, all of that. And maybe one of the purposes of those ratios is to quantify the curvature. So how much of a hump I have in here. But here's a problem, because this is another pattern, pattern B, and has exactly the same magnitude of a hump. So the distance between here and here is exactly the same thing as here and here. And I know that because this is how I made those patterns. But when you look at the ratios, for example, lanthanum over samarium, which is what we used in the previous slide to kind of estimate our a curvature or this hump here. Here we have 0.025, and here we have 0.43. That's more than an order of magnitude difference. Okay, so this is also another problem. So not only that those ratios are non-unique, they're also not independent, because when we look at this ratio here, it has lanthanum in it. So even though we're actually interested at what the mid rare earth elements are doing in samarium, because there's lanthanum in the equation, whatever lanthanum is doing, that influences our estimate for the this ratio and essentially what the mid rare earth elements are doing. There are ways around it. So for example, there's a way to try and address that. So instead of looking at lanthanum to a ratio, we're looking at a ratio relative to an interpolation. So there's a measure, it's called dysprosium over dysprosium star. And this looks at how far away is dysprosium, this element over here, how far away it is from the line connecting lanthanum and ytterbium. So there's pattern D, which for some reason I guess, so this is pattern D. And here's lanthanum, here's ytterbium. This is the line that connects them, right? And dysprosium plots on the line just by chance, because dysprosium star is 1, and then it is not informative. It doesn't actually tell us anything about the pattern, because if we didn't see it, we would think it's a flat pattern. Current connection is unstable. Can you all hear me just fine?
We lost you for a second, but I think it seems okay again.
Do you want me to repeat anything?
I think I followed all of that.
Okay, that's fine. Yeah.
No, I think it's okay.
Well, if you lose me again, then let me know, because Australia is infamous for its bad internet. Which is what you would expect for a modern country. Anyway, okay, so we have all of those issues with element ratios. They're not independent, they're non-unique, they only make sense if you also have the earth elements pattern to look at, which kind of defeats the point of having that, because the entire idea is to take a bunch of patterns and convert them from lines into points. So then you can do something with that. Now, when you look at patterns, so the ones that are on the screen now, you you see that, well, they're kind of smooth curves. They go up and down in a smooth way. And that is happening because of what we heard from McCallum, that, you know, the ionic radius and the chemical components. So here's an idea. How about we try to fit a polynomial to those lines, okay? And then the idea is, if we have a pattern that looks something like a linear, like a line, so that is a function that maybe can be described as an x. If we have a parabola, then we have an x squared. If you have something like this, then we might have an x cubed, okay? And by using that, we might be able to kind of parameterize the patterns as a whole. So instead of looking at a certain element or a ratio of two elements, we have a number, you know, so we might have a coefficient here, let's call it a, for example, that tells us what's the degree that our pattern looks like this, or this, or this. Now, this is a very nice idea, but it's easier said than done, and I'll show you why. Here's a line. So here's a function of a line, this thing, and the number that we care about here is this, it's 2, because 2 is the coefficient of x, and it tells us what the slope of this line is. So if we have a higher x, a higher coefficient, it's like that. If we have a lower number, it's like that. If we have a negative number, it's like that, okay? Okay, that's all nice and well. Let's see what happens when we have a parabola. So here's a parabola, exactly the same xy space, so from 2 to 3 and -1 to 1, which is what we had before. And this is the equation for that, which is a bit more complex. And as before, we have 2 here is the number that describes, let's say, the width of the parabola. And all of those numbers, the x and the constant, they just shift it around in space. Okay, now let's try to combine both of them into one function. So we have a line, we have a parabola, or a quadratic function, and when you combine them, they look like that, which is actually good. It's a parabola that now it goes up, as you would expect. But the problem is that when you look at the new function, this number is no longer 2. So even though we have something that in general it goes up, the number that we expect to describe the linear slope is now -9, which is now 2. So this would be 2, this is -9. So that's not good. So this means that the polynomials, the functions that we have here, are not orthogonal. It means they're not independent of each other. Anything I do to the parabola will change all of this. So the idea is that we want to find orthogonal functions, and orthogonal functions are those where we can change all of those numbers independently of the other functions, okay? So for example, here we have a new function where we have, you know, one function of x, and somewhere in that function we just have x. Then we have another function, and inside somewhere we have an x squared, and inside here we have an x cubed, okay? And it is possible to find those functions. You can read Hugh's paper, and me and Morgan, we have a paper that we submitted a couple of days ago. Hopefully it should be out not in too much future, and we have a slightly more detailed description of what the functions are. The good thing is that you don't need to know what the functions are. Now, this function will give you some kind of polynomial in y and x space, but because we're dealing with reference patterns, we will rename those things and give everything different names. And now we have our elements and R, which is the ionic radius. So we start here with lanthanum, this in here at the end, and then we have some kind of polynomial that is the reference pattern. Now, something important to notice here is that this is natural log, and usually we plot those things on log 10, but the transformation from one to the other is pretty much a trivial thing, but something to keep in mind. So the point about those orthogonal polynomials is that this function, for example, will describe something that looks like this, and I can change this number. I can change lambda 3 as much as I want, and it will not matter at all for all of those other functions. Okay, so we're taking a pattern and we're decomposing it into shape components, a line, quadratic curvature, and all of those. The other thing is that because they're orthogonal, which is the independent of each other, we can just neglect some of them and it will not change the others. So for example, let's say that I don't want this one, I don't like it. I can just not use it and it will not change anything for all of those other ones, okay? Now, how do these functions look like and how do they work? So I'll show you the first app, and that's the web address for that. Available online, free to use. You can use it now if you want, and just look. So when you go there, this is the app, and if for some reason you forgot the web address or you don't have it, you can just go on Google and look me up or something, I think, and yeah, it's the first result, the software here, and those are the things. I also made an oxygen efficacy buffer, a calculator, for those of you who care about this stuff, so you can go and have a look. Anyway, that's the app. And this is an app that's a rare element pattern generator. It allows you to take lambdas and make patterns out of it. Show an example. So just click this set to 0 button here. Here's a pattern. All of the coefficients are 0, so it's a horizontal, flat pattern, not really interesting. Lambda 0 is the overall abundance average of the rare elements. So see, as I increase it with my keyboard, the line goes up and goes down. Lambda 1 is, like we said, the linear slope. It can go up, say 15, or it can go down. I can have a minus. And it's all interactive. You know, you can just play with that. Okay, so we have this. Let's have a look at how a lambda 2 might look like. So it's a, let's give it a bit more, maybe 300. So this is a quadratic curvature, and I can add a minus and it goes the other way. A lambda 3 would be this, too much, let's just scale it, this sinusoidal shape, and a lambda 4 would be some kind of M shape or W shape, depending on what numbers you put in there, and you can add all of them together. So just I have some preset patterns here of how an might maybe look like. So I'm just pick an apatite because that's my favorite mineral. So here's a pattern that is constructed using those parameters. So we have number 0, 5, number 1, and we have all of those numbers in here. I also included a made up European anomaly. Okay, so that's the app. And if you want, if you scroll down here, you can also have, there's a download data button, and it shows you ppm and what you get when it's normalized to all kinds of different things. Okay, so this is the app. Let's have, go back to the presentation. Where was it? Here, oh, this. The other thing it can do is it can give you a better estimate on your serum and your opening anomalies. So here's an example of a pattern that looks like what you might expect from zircon. So zircons are very famous for having huge differences between the light and the heavy earth elements. You can have 5 orders of magnitude difference on a logarithmic scale, right? And the traditional way to calculate anomalies, cerium and europium anomalies, is you calculate something that's called cerium divided by cerium star, which means your measured cerium, for example, this thing, divided by the square root of lanthanum and praseodymium. So, which is the geometric mean. It's a kind of interpolated line on a log scale. So it's this line in here, this light blue line. So then we say, well, let's take the ratio of how much cerium we actually have to how much cerium we think we have if we interpolate the line, this place over there, and it gives us a number. But this is a linear line and our pattern is curved. There's some curvature here. And let's say the real cerium contents, if you didn't have an anomaly, would actually not be on this line. There would be this blue circle here. And it may look like there's not a lot of difference there because, the lines are almost overlapping, but that's an artifact of how we display the patterns. So in this case, it's a log scale spanning 5 orders of magnitude. I will tell you that in this case, the cerium anomaly, when it's calculated relative to the interpolated line, is 20% higher than what it is calculated relative to the, let's say, the correct curved place where it should be. So we're talking about 20% for the cerium anomaly, which is quite a lot. Same thing with europium. You have exactly the same problem. Europium or europium star. You have to take europium and square root of samarium times gadolinium. That's a D. In here, the difference is about 10%. So we're underestimating our europium anomaly by 10%, which again is quite a lot. And if you use that to calculate things like oxygen fugacity or something, all of this, that's a systematic error, which is also not independent because again, it depends on the curvature. That just propagates through your calculations and it gives you the wrong answer eventually. Just go back to our made up appetite here. So you can see that the pattern is designed such that there is no cerium anomaly. So this is 1. I'm telling you that I want this pattern to be 1, you being the app, yes. And but when you look at the interpolated cerium anomaly, you see that see it with your eyes. If we take a line connecting lanthanum and praseodymium, cerium plots below it. And yes, you do get that. So we have 0.784, and that's not real. There is no cerium anomaly in this pattern. I can make a cerium anomaly. Let's say I make this 10, and now we have a cerium anomaly. Then this tells you, oh, it's 7.84, which is not real. It should be 10. Same thing with europium. So again, in this case, we have about 20% difference. Okay, let's go back to the presentation. So I think that so far I convinced you that lambdas are a good thing because they're independent. I can change a certain shape, linear slope or quadratic curvature, or whatever, and it doesn't change the other ones. It's unique in that any set of lambdas uniquely defines one single rare thermal pattern. If you remember in the beginning, I showed you how for a certain lanthanum to lutetium and lanthanum to samarium ratios, you can have more than one patterns. Not the case with lambdas, they're all unique and they are consistent. So our choice was to use the O'Neill values for the normalization and not allow any other values. So then it's consistent. You always have the same lambdas, and and that can be in igneous rocks, metamorphic rocks, sediments, Mars, the moon, seawater, river water, dust, anything that you can get reference patterns out from. The lambdas will be comparable across all of them. Yeah. Okay. Now, so far I showed you how the lambdas look like. Let's have a look at how we actually go about getting data out of patterns that we have. So for that, I have the second app, which the only difference is there's a B instead of an A. I'm not very original with app names. And it's this one. So when you open the app, you have this screen that has some sample data to begin with down here. So all of those are ppm values of patterns. And you can click one and it shows you the pattern. You can click the other one, it shows you that one. And to show you some things, let's have a look at a large database. So I will upload, should be here and in here. Let's upload this database of 616 real-time patterns. And as you can see, here are a lot of patterns, okay? Each one of them in here, you can see it has lambdas. So lambda 0, lambda 1, lambda 2, lambda 3, and lambda 4. So those are the lambdas for each of the patterns. It has some statistical things like R squared, so how good the fit is. We can go to the right and see that we can have standard errors on the lambda, so we can have error bars. For those of you who care, there are also p-values. Whether you should or not use them, that's up to you. We have the ratios of the measured elements to what they should be from the fit. And for example, for things like europium, this is actually telling you what the europium anomaly is according to the lambda method. So taking into account the curvature. Other things you can do here, you can have a look at a lambda plot. So for example, let's have a look at, click this tab here. And we would like a lambda 1 and lambda 2, and why am I not seeing anything? This should work, and it doesn't. Let's try to reload the thing. Let's get this database again. And there we go. There we go, it works now. So we can have a lambda 1 and a lambda 2. So here's a database of 616 mid-ocean ridge basalts. And you can see that, well, here's some kind of an array or a trend. And just by looking at this, this is already telling you something about mid-ocean ridge basalts. Because when you think of them, it's very common to say that we have two types of morbs. We have E morbs and H morbs and D morbs, so depleted morbs. And in this case, we can see there's a continuum. There's a, it starts in one place, it goes to the other place. Now, because we don't really remember what does -5 lambda 1 and something, all of that means, so it's very easy to just flick through to the other app, type in those numbers. So we had -5 for lambda 1, had -50 or something for lambda 2, we can scale, and this is a depleted morb, okay? Then we can look at the top here, on the top left, and then have 1 and maybe 40, 10 and 40, so we can go there, and maybe let's do a 40 here. And this looks like an enriched morb. So, yeah, I mean, I think it's a wonderful example of showing, there aren't two types, there are two end members. The other thing is we can even tweak a bit our patterns by, let's have a look at lambda 3. And we can see that a lot of them, most of them cluster at around maybe -200 for lambda 3. So we can take this, add -200 to the lambda 3, and this is a pattern that looks a bit more like a typical enriched morb. And the good thing about it is that it shows you really a pattern that doesn't really exist, because there is no pattern that is exactly 10, 40, -200, and 0 for lambda 4. So each pattern will have their own, small variation in lambdas and uncertainties, elements that for some analytical reason are a bit off. So instead of just looking at one specific pattern out of those and then getting a bit of bias, we can just make up our own pattern that looks like a representative, very simplified version of those patterns that we care about, just by doing nice round numbers and nothing else. Okay. Now, to do this, there is an assumption that our real-time patterns can be represented by this smooth polynomial curve, right? Because otherwise, how do you fit something? So here's an example of patterns from Tungi, which is an ore deposit in Australia. And when you look at those patterns, they don't really look smooth. When you look at it, it's a bit hard to visualize how these things will be fitted well in the method because, you know, it goes up and down and all kinds of anomalies and stuff like that. So it's a bit challenging, but this is an artifact of just how we plot them. Because first of all, there's yttrium here, which gives us this hole in here. And again, it's not a lanthanide, it's not in the patterns. You know, we have anomalies, europium anomaly, maybe there's a cerium anomaly. It's not plotted according to ionic radius, and there's no gap for promethium, which should be here. So let's take their data and try and fit it and see what happens. So back to the patterns. It's this one. And let's have a look, for example, at this pattern. And you look at it, and it looks, the fit is kind of okay here. So there is to you can turn them off and on if you want.
Sorry, Michael, we just missed that last sentence. Sorry, just cut out for a sec.
Yeah, okay. Oh, and now I'm getting the message that it's unstable. So I think it should be okay now. Yeah.
So the last thing we heard was the fit was good.
Okay. So the fit is mostly good. And again, just to say that what we're looking at, so the black line, that's the fit, that's the polynomial fit. The gray line in the circles, that's the data. And we can turn them off and on with the buttons here. Yeah. Okay. Let's look at a different, actually before we look at a different pattern, we can also say that, well, you know, in here, cerium looks a bit anomalous, maybe not. So we can choose to exclude cerium from the fit, and then it doesn't take that into account for the lambdas. And you see that when we do that, the fit is actually much better because it was trying to fit something that should not have been fitted in the first place. I think a good example is what happens if we try to fit europium into the lambdas and then have this awful fit that doesn't follow the data. But then if we tell it, don't fit a europium, it's actually pretty good. So look at this, maybe a different pattern. So this one that someone on Twitter said it looks like a dinosaur, which yeah, pretty much. And even though we have a pattern that, you know, at the first glance, it didn't look like it would make a good fit, it actually does. And the things that there's a slight misfit with gadolinium here and samarium here, this will something that I can fix later on, and we will get there soon. Okay. Let's take a look at a lot of data. So we have a student in a group, Ross Chandler, who's working on ore deposit from the Mount Isa region in Australia. So he has a bunch of scans, he has a bunch of ICGs, and what he did, he took all of those patterns from those deposits and plotted them all together. You see, there's this huge jumble of many patterns, and if you look at it for a while, then maybe you can see that the ICGs here have positive europium anomalies, and the scans in here, they have maybe slightly more light earth elements than the others. But it's a bit hard to see what's happening here because there are so many patterns. We can try and split them, which makes it a bit easier to see what is happening, and we can split them even more. And then it's even easier to see. But the problem is that now, because we're not overplotting them, it's hard to compare one to the other because we have this one over here and this one over here that they look maybe kind of a bit similar, but they're so far away, it's a bit hard to tell what are the common things and what are the differences. So let's try to plot them in a different way. I think what's immediately obvious is that the europium anomalies, they're all different. So let's choose the europium anomaly as a y-axis. And our x-axis would be either lambdas down here or those element ratios that we have up here. And when you look at them, so this plot here, lanthanum over lutetium, looks very similar to lambda 1, which makes sense. It's kind of what we expected because lambda 1 is the linear slope, and unless we have really bizarre things happening in the patterns, then lanthanum over lutetium tells you exactly that. Something that you can see, though, is that in the top plot, it looks like this is on a trend, and this is maybe on that trend, maybe it's a different cluster. In the lambda 1 plot, they look a bit closer to being on a trend. Okay, so it's a bit less noisy. When we look at those two plots here, so the ones that are trying to tell us what maybe the quadratic curvature is, they do look very similar, almost identical, but there's one very important difference. And I'd like to draw attention to the blue circles in here. So this is one of the scans, and in our lambda 2 plot, they have the lowest lambda 2 values, which means they have the lowest amount of quadratic curvature. You can go back and look at them. It's this one, and yes, indeed, it looks pretty close to a straight line. Unlike this one, which, let's see, curves a bit, or this one, which curves a lot. But we don't see that in the lanthanum over samarium. It plots actually higher. And this is, again, that's the problem of independence, because we have lanthanum here. So whatever lanthanum is doing, it's affecting this thing here. So we have kind of a linear slope, this one and this one, and we have our quadratic curvature. And the quadratic curvature is to the left, the linear slope is in the middle, and this is in between. So it's kind of blending both of them together. And that's the point about the orthogonal polynomials. They don't depend, they're independent. They tell you things that unrelated to what other shape features you have in your reference patterns. The other thing is this thing. So when you plot them with lambda 3, you get a beautiful trend or pattern or shape. And I have never seen that before. I don't know what it means, but this is interesting. The first thing to understanding some kind of process is seeing that the process exists. And in here, you might say, well, our scans and IOCGs meet at lambda 3 of 0. So maybe there's a common source, maybe they're coming from the same mantle source, and then there's some kind of different fractionation trend or different fractionation minerals or different fluid chemistries. Those are things that we can think about. And to think about them, we first have to know that this is something that happens. And I think this is a wonderful example. And when you look at gadolinium over lutetium, it tells you absolutely nothing. And now we can also do lambda plots, okay? For example, lambda 1, lambda 2, 1, and 3 over here. And those are all deposits, right? We have scans and IOCGs. And let's say you have an exploration campaign in Mount Isa. So you drill into a potential target and you hit this kind of alteration zone. And you want to know, is this an IOCG or is this a scan? Because some elements, like maybe cobalt or tungsten, might be associated with one type of ore deposit or the other type of ore deposit. But you're only in the alteration zone. You haven't hit the deposit itself. So you might take your core, you send it to assay, you have real-time data, and then you try and plot it on the top graphs and see if it helps you. So let's say you get a result, which is here. Is this a scan? Is this an IOCG? You have no idea because they're all together, right? They're not independent. They're kind of all mixed together. But when you look at the lambdas, other than lambda 1 and lambda 2 plot, which isn't really useful, we actually have a beautiful trend here. And all of those, they're very separate. So you can plot your new data on this and then have a better idea because there's no overplotting. The lambdas completely distinguish, other than maybe an outlier here, but they completely distinguish IOCGs from scans, which is a very nice thing to be able to do, and it would be very hard to do it if you didn't have the method. Yeah, let's move on. Now I'll talk about something a bit more advanced. This is something from the Hugh Neal paper that I showed earlier. This thing here, so this is the MORB array, the mid-ocean rich basalt array that I showed you in the app earlier, and you have it everywhere. On top of that, we have those things, which are tholeiites from Hawaii, and all of those other things are OIB, so ocean island basalts. First of all, you can see that when you plot them in lambda 1 and lambda 2 space, you see that they plot in different areas. So it makes it immediately obvious that there's a different chemistry happening there, okay? And all of the OABs, they plot in different areas, and they have a sub-parallel trend to MORBs. So this goes like that, they go like that, kind of. One way to explain that is, let's say, by low pressure fractionation, which is what's responsible for this in the MORBs. So you have some magmas erupting, they're in a shallow magma chamber, and then they're doing all of that. The question is, why do they all plot in different areas? Or this one here. And can we kind of model this or try and find something that helps us understand the process that made it or the mantle source? And to do that, let's have a look at partition coefficients. So here are some partition coefficients for the earth elements between forsterite and silicate liquid. And partition coefficients can be parameterized using the lattice-strained model of London wood, in which we have a square, like a radius square term and a radius cubic term, which looks kind of very similar to what we have with the lambdas. So it means that we can fit partition coefficients to the lambdas as well. Then we can use that to make kind of arrows and vectors and all kinds of things on the diagram to help us understand what is happening. So here's an example. If we take batch melting of garnet peridotite at 40 kilobars and we do only 1% melting, so our F equals 0.01, and we start here, we will get something at this end, okay? Now, the thing is that what you get at the end is a function of two things. One is the process. The other one is what you started with. And the process, so batch melting of garnet peridotite at 40 kilobars, is represented by this arrow, this vector. And this will be the same thing regardless of what you start with. So then you can maybe do something like this. Just go back here. You can actually take this arrow and move it. And this will be correct. So let's say that you want to get something that looks like Hawaiian foliites. Just take your arrow, do exactly the same thing, same process, but instead of melting something that looks like primitive mantle, which would plot at around 0, 0, you're plotting something that's more depleted, okay? So here's one simple way of using those process vectors. Back to the presentation. There are all kinds of different process vectors. You have them for fractional crystallization, you have for mixing, the fractional accumulated batch melting, recharge, all of that. And there are all kinds of ways in which you can model all of the things. Those are the three polynomials, and they're described in the O'Neill paper. And just for example, you remember those OIBs that were in here. We had those different arrays, so they can be explained by just melting at different pressures, because this one is 30 kilobars, this one is 40 kilobars. So this is a very nice way to look at those processes, which would otherwise be very hard or challenging to do without that, because when you do those modeling, what you actually do, you have your patterns, you have your measured pattern. Then you say, well, if I have 1% of melting, I'll have this. If I have 2% of melting, I have this. If I have 3%, I have this. Then you kind of compare and try to see which one looks more like your data. And again, in this case, we're looking at lambdas, and it's capturing all of those curvatures and shape components you have for that. Let's just have another look at the Hawaiian foliites. So here's a certain process, and we can line and move it down here, and then we can show that we can melt garnet lersolites at 30 kilobars at 5%. And if we start with this composition B here, so a depleted source, this is how we might get Hawaiian foliites. Okay. So all of this is described in Hugh's paper. So be sure to read that if you find that interesting and something that you want to do. The last thing I want to talk about, because I have only a couple of minutes left, is the tethered effect. So the tethered effect is a very interesting thing that we sometimes see in real-time patterns, where all of the elements, all of the 14 elements can be divided into 4, and in each group of 4, there's some kind of certain fractionation or trend or a parabola. So essentially, I'm talking about this. So here's tethered 1, here's tethered 3, tethered 4, again, tethered 1, tethered 3, tethered 4. Not much that we can do about tethered 2 because we don't have the promethium and we have the europium anomaly. And one of the problems with that is that there has been and there is still some kind of a debate in literature whether this is a real thing, whether it actually happens, or we just have noise in our data, or our analyses are not accurate enough. So I'll just show you in A lambda R. So first up, how this can be done. There's a tab that is a tethered effect, and you can just make up your own tethers. Here. And here's another tether. So this is how a pattern with very strong tethered effects and nothing else would look like. Not really smooth, but all of those shapes are actually determined by the quantum chemistry. So it's a real thing. The thing here is that a lot of the methods used to measure or quantify tethered effect are based on the same idea like cerium or europium anomaly. So you look at the difference between the the elements in the middle and the elements on the side. And again, if you have curvature, so let's just look, for example, this one, where there's no tethered effect, and all of those measures from the literature, they're either 1 or 0, so that's good. It doesn't see a tethered effect. But then if we don't have a tethered effect, but then we start to have some kind of curvature in our pattern, so here is some curvature, then even though there is no tethered effect, it starts seeing things, okay? Though those numbers are not 1 and those numbers are not 0. So the good thing about the fitting app is that it can also handle those. So it can fit curvature and tetrads at the same time. Now, you remember this dinosaur-like pattern from earlier, and I said that, yeah, look, there's a bit of a problem with gadolinium and samarium. They don't really fit. Well, we can fix that because this is a low temperature alteration with very exotic fluid chemistry, so exactly the thing that you would expect the tetrad effect to happen in. And if we fit all the tetrads, let's have a look at this. There is a perfect fit. This is wonderful. I'll show another example when seawater. So with seawater, there's also a debate in the literature whether seawater has a tetrad effect or not. So this data, this is seawater normalized to chondrite. It's usually normalized to sediments or pus, but in this case, I'm using chondrites. And the curve looks kind of okay, but not perfect. We can fit tetrads, and it just makes the pattern fit perfectly, okay? Now, you might be thinking, well, of course, there will be a better fit because I'm fitting more parameters. And we all know that the more parameters you fit to a pattern, even if it doesn't fit really, even if your model isn't real, it will have a better fit. So we can check all of those things for consistency. So that's just looking at the tetrad parameters. I fit it for seawater, and we can see that they are all significant, statistically significant, because the error bars are far away from the 0 line. They're all about the same magnitude and the same position, except lambda 1, tetrad 1, sorry, which is geologically known to be stronger. So it kind of looks like what we expect. It's consistent with two different analyses. We have exactly the same thing, so it's most likely a real thing. Okay, but it's always good to remember that you need to have some kind of geological understanding of what you expect, and tetrads break the orthogonality of the lambda. So always be careful when you're doing tetrads. There will be more details on that in the paper that we submitted. I think that's almost everything, but just one thing I forgot to tell you in here, that those things, I'm focusing here mostly on lambdas and real element ratios and European anomalies, but the correlations can be between a lot of things, right? So it doesn't have to be Earth elements. And the student who's working on this, he told me that some of those lambdas correlate with geophysical anomalies. So you can have a magnetic high associated with a certain lambda. You can plot one axis your lambdas, and then the other axis you can have, isotopes. You can have, all kinds of different elements. You can have latitude, longitude. If you're talking about weathering, maybe average precipitation. You can have all kinds of different things to try and see if your lambdas correlate with that, and then it might help you learn new things about your data. Okay, and this is all very new, so I'm pretty sure that you can use in all kinds of applications and find new things that I haven't thought about them yet. Okay, so I think that's all I wanted to say, and I'm just out of time. So thank you very much, and I'm now happy to take any questions.
Brilliant, Michael. That was genuinely supremely cool. That is amazing. I absolutely love this. I'm so excited to actually start putting some geochem in there, basically. I love the lambdas, looking at different parts of your ore deposit system. That's going to be really interesting, and I am looking forward to using it. I think we had a question earlier from Casper, I think, on that, asking a question about distinguishing between ore deposits. Casper, do you still want to ask that or discuss that a bit more? You want to unmute yourself? Casper is still here. Okay, well, do you have any further comment on that, Michael? Yeah, I mean, you did obviously go through distinguishing deposits or different ore deposits, but what about within a deposit? Can you distinguish zones, for example? Do you think?
Maybe.
Maybe.
Go ahead and try, and if it works, then it works.
We'll find out.
I spent most of my time developing the code and the math, and I haven't applied it myself to a lot of ore deposits, but I'm pretty sure that it will show you things, because so far, almost in any case that I use it on something, it told me something that I didn't know before or I didn't see before, like that thing with the IOCG scan lambda fit trend. So go ahead and try. I mean, it's the app is available online. There are instructions there on how to upload your data. The fitting takes 5 seconds per 1,000 samples. So it doesn't take long.
Question: is that mineral chemistry or bulk chemistry? Anything
that has a reference pattern. It can be rock, it can be mineral, it can be dust in the air, it can be seawater, it can be river water, it can be pull your tooth out and measure that. It can be anything. Anything that has a reference pattern in it will be modeled by that.
That's a good point. How much rare earths are in the appetite in your bones? I don't know. I would like to know.
Yeah, exactly.
I will find out. I'll get back to you. If Jane Barling is there, would you like to ask your question?
Hi, really interesting. And I was delighted to see Heard Island in the O'Neill plots, so he's so often forgotten. I guess you partly answered my question as you were going forward, and that was just to what extent you know that the anomaly that you're modeling based relative to your curves is more chemically or geochemically significant than just plotting them as a numerical value relative to a linear interpretation. But as you progressed forward, you kind of answered that, I think.
Okay. Yeah, look, the thing is that patterns are curved, okay? And if there's a curvature in the pattern, there's no reason to think that just between lanthanum and praseodymium or samarium, this is just by chance, it will be linear. I mean, it should also be curved because all of the earth elements, their properties vary in this consistent way because of the ionic radius, because of the F electrons. So if your pattern is curved, then I do expect that this will happen. If your pattern is not curved, so lambda 2, 3, and 4 are 0 or very close to 0, so it will not make a difference.
Okay.
Okay. So Julian was happy that you addressed the tetrad effect, so that's fine with that. I think
I saw the question on the chat, and the answer is yes, you can do tetrads.
Yes, no, and he later on is like, yeah, okay, got it. Thanks.
Okay.
So I next have a question from Amory Ladwig.
Hi, I'm here. I think my question has been answered during the talk as well. Like it came up in the following slides. So, yeah, that's fine too.
Okay.
Thanks.
Yeah, I can see your question, and you were asking about the gadolinium to terbium ratio. So again, the thing is that because element ratios are not independent, no, it's impossible to talk only about the gadolinium and terbium ratio. It has to be talked about in the context of what the gadolinium is doing and what the terbium is doing. So would it be equally similar? Maybe, maybe not. It depends on your data and depends on your luck. The thing is that the lambda 2 will always be independent of the other thing. So it will always work.
All right, thank you.
I have a question from Anthony Lanati, which I think he wants me to ask. Speak now, if not. No? Okay. So can you outline if there are any limitations of the method you've come across when using the lambdas? Also, are there any advice you can give to make sure we use them correctly?
Okay, so hi, Anthony. I'm hoping you're enjoying the winter in Germany. It's nice and summer fun here in Australia. To answer your question, yes, there are limitations. Some of them will be in the paper that we submitted, where we talk about some of the complexities. You can minimize limitations if your data is good, because this is a mathematical model, okay? Garbage in, garbage out. So just try to have your data to be as good as possible. And this is especially important, for example, when you have very strongly light earth element enriched patterns, because when you have samples like that and you measure them, for example, by ICP-MS or laser, very often you have oxide interferences. So you will have all kinds of erbium anomalies, gadolinium anomalies, all kinds of weird different things that aren't real. They're happening because of oxide interferences from the light earth elements. I have in the supplementary of one of my papers on Norman's bow, I have a part where I'm addressing that. I can send you that later. So that's one thing. Europium anomalies, there's a very strong interference from barium. So if you have 5 weight % of barium in your sample, and then you're seeing a positive europium anomaly, it's probably not real. Or it could be, you don't know. When you have tetrads, so tetrads have a tendency to clash with lambda 4. Okay, so if you're fitting tetrads and you have a strong lambda 4, maybe it's better to untick the lambda 4 option to see how it looks. Yeah, and I think the limitation, always remember that this is a mathematical fit, okay? And it's we built it in such a way that it's very convenient to use it as some black box where you put in numbers and you get numbers back. Always important to think, are the numbers that I'm getting, do they make any sense? Is this what I'm expecting? If it's something that I'm not expecting, is this an analytical problem? Is it a problem with the fitting? By the way, this is very new software, and if you manage to break it, please send me an email and I'll try to fix it. Because we had a bunch of undergrad students who had some projects doing laser ablation analysis of melting inclusion. So they had very small spot sizes and the data were just awful. And then they told me, oh, look, when I upload my data, it crashes. And like, yeah, well, it's because your data was so bad that it didn't even handle. So I fixed that. So if something is not working or not giving you the result that you think it should give you, send me an email or find me on Twitter, whatever, ResearchGate,
Okay, Michael, you have a lot more questions. I'm gonna butt in there, and you can ask it. So, from Julian Alas, would you like to ask your question?
Yeah, sure. Thanks first for this great talk and this great tool. My questions was about the error. I saw on these Tethered Effect plots that you had at the last slide that you put some errors. Are these actually representing averages of multiple measurements, or is it actually an error on the fit?
So you're talking about the error bars they had on in the individual coefficients.
Yeah.
That's the uncertainty on the fit itself. Let me show you. Share my screen. Let's go to the app. So in here, for each parameter, there's a this thing. Okay, can you see this?
Yes.
So it's the uncertainty that you have on this specific parameter for this specific pattern, and just take something that has more patterns. When you plot them, so see there are error bars, right? So those error bars are this thing, which is what I also plotted there.
Okay, excellent. Okay. That's very good. Thank you.
Okay, one last quick question from Adrian, and then Michael, if you don't mind just addressing the other few questions in the chat, would that be okay?
Yeah, that's fine.
Yeah, just keep everyone on time because I know people have other commitments.
Hi, Michael. Thanks. It was a great talk. So it was just a quick question. My head is aching trying to work this one out for myself. But if you make a fit which is as sophisticated as the fitting you're trying to do, that implies that you've actually modeled your data points absolutely perfectly. And correct me if I'm wrong, if the model isn't correct and you're trying to fit things, then your data, your parameters no longer they cease to be independent. And so if the system is struggling to fit the data, then you find false correlations between the parameters. Now, the reason I'm asking this question is that obviously the strength in what you're doing is when you take a very, very large data set and you crunch it all up and you analyze it, and that's wonderful. But when you lose that ability literally to almost massage and eyeball every single line that you're looking at independently, then you run this potential that there is some, if you like, artificially generated relationship between the parameters, which is due to the quality of fitting. Now, have I got that right, or am I missing the point here?
So that's the thing about the polynomials being orthogonal. They're predetermined so that they will not correlate. Okay, there's a mathematical way to derive them. It involves a lot of matrix math and linear algebra. But the idea is that they're independent of each other by design. Okay, now
but surely that only works if the fit is perfect. So if your data fit absolutely perfectly, then they're independent. But if the data are struggling, if the fit is struggling to fit things, then I think, as I understand it, they cease to be independent.
No, they're still independent, but the thing is that look, of course, there is an underlying assumption that rare element patterns in nature can be fitted. Okay, so they can be described by the model, which is always an assumption when you're doing mathematical modeling of observations in nature. The thing is that when you have good data, okay, so things where you don't have any interferences and things that were analyzed properly and the standard errors and deviations on your data are very low, I haven't yet seen a pattern that doesn't fit well. I mean, my R squared, the adjusted R squared, so it takes into account the fact that we're fitting a lot of parameters, it's always greater than 0.95, okay? And for those that didn't, and then you fit tetrads, there was, which then improves the fit, there was always a geological reason for having tetrads. So you don't just go and fit anything and put all of your parameters and hope for the best, right? And yes, it depends on the quality of the data. Garbage in, garbage out, right?
I take your point, but you've only got 13 data points in a run, and you're fitting them with 6 variables. So your R squared is going to be 0.95, even if the data are almost even if the data are random. So the quality of the fit is really an issue there, because as I get it, listen.
Yes, you're perfectly fine, but what we see is that the quality of the fit in all of the things that I worked on so far was good enough. And you can look at Hugh's paper. He has about 10 or 15 pages just describing exactly what you're talking about. The quality of the fit, is it, I know all of those statistical issues, it's in there, and you can read that. And then if you still have any questions, you're more than welcome to ask me or Hugh, because
Sure.
you're audience, not me.
Okay, cool. I might have to stop the Q&A there, because I don't want to overrun and impact on everyone else's day or evenings as well. And there are definitely plenty more questions if you don't mind addressing those in the chat, Michael.
Yeah, sure. Look, and you can always email me. I tend to answer to everyone, and if I didn't, send me an email again, and I will answer you. And I try to do it within a few days. Okay, so.
Brilliant, thank you, and thank you so much, Michael. That was genuinely fascinating. Really interesting to know more. One small thing just before we start with Morgan is that, in case you missed it, we would just really like, for our own internal purposes, to know what country you're from, what you normally study, and if you'd like to be on a mailing list. And then I've just put a link in the chat if you wouldn't mind clicking on that and letting us know. You don't have to join a mailing list if you don't want to. Just to know where you're coming from. It's just for our own kind of internal statistics. Anyway, great. Thank you very much, Michael.